Chapter 9, Principal Component Analysis. This chapter begins with the singular value decomposition. The SVD is now the standard way to carry out the principal component analysis. After studying the SVD, we'll consider an application to least squares problems. Then finally, we'll consider the principal component analysis. Let's go to section 9.1, singular value decomposition. Okay, we have a theorem. A is an m by n matrix with m is larger than or equal to n. Then we can write A as U sigma V transpose. Here, U is an m by n matrix satisfying U transpose U as identity. So once m is the same as n, then U is an orthogonal matrix. Now V is a square matrix satisfying the property V transpose V is identity, so that V is an orthogonal matrix. Sigma is a diagonal matrix with singular values decreasing order. It's a non-negative, but quantity is decreasing. Let's see the illustration pictorially given. A is a tall matrix and U has the same size. Sigma, a diagonal matrix, square matrix, and then V transpose is also a square matrix. Here, U is an m by n. It's not officially, rigorously orthogonal, but because of the property U transpose U is identity, we conventionally say that U is an orthogonal matrix. That means here this property is satisfied. Anyway, U is the left singular vectors because it is the left side. And now sigma is square diagonal, and the matrix is just having the singular values of A. V is now square really orthogonal matrix, and that is called the right singular vectors because on the right side. Okay. For some r less than or equal to n, the singular values may satisfy this equation here. From sigma r plus 1, everything else over there, remaining singular values are 0. And sigma r is the smallest non-zero singular value. Then in this case, we say rank of A is R. Here rank means then the number of independent columns in A. So once so sigma R, rank is R, then there are only R linear independent columns in A. M is smaller than n, which means A is a flat matrix. Then the singular value decomposition can be defined by considering A transpose. A transpose must be now tall matrix, right? Here we have proof for the theorem, and using the mathematical induction, we can prove that. And I'll not cover the proof, but if you are interested in mathematics, then why not? just try to follow step by step. It'll be a good mathematical practice. So just try to follow the proof, and you can learn something. Okay. Interpretation of the singular value decomposition. Okay. Here we start with algebraic interpretation. Rank is R, and A is U sigma V transpose is the singular value decomposition of A. Here in detail, U is now from U1 to UN, n columns, and sigma is diagonal metric along diagonal entries given singular values, and V is now n columns. And here, this one, each one has length n, but for U, each vector column has length m. Okay. Sigma R is the smallest positive singular value. Then here now, that is a singular value decomposition. And then by multiplying V right side, we have AB is sigma U sigma V transpose V. That's the identity, so that U sigma. We consider detail AB. That is metric multiplication. It's the basic idea in linear algebra. So the A will be multiplied to each column. So we have that result. Now for U sigma, we write here U and sigma. This diagonal multiplication, the metric multiplication, will make column scaling. So the sigma 1 will multiply here U1, sigma 2, U2, and so on. So we have this result. From this equation, we can see a V1 is sigma 1 U1, a V2 is sigma 2 U2, and so on. Now, except this R, we start with the assumption that rank is R, so that from here, that will be 0, because over there is 0. Now, so from this match, we can see ABJ is sigma j uj for j's from 1 to R, and then AVJ is 0, the 0 vector, for j from R plus 1 to n. Similarly, for A transpose, we can get this result. And A transpose Uj is sigma j Vj, and for j's from 1 to R, and A transpose Uj must be 0. We got these two two sets of identities. Now, from this one, we can further match one step. Okay. Now, Vj, sigma j squared, eigenvector, eigenvalue of A transpose A. We can check it quite easily. We already know that AVJ is sigma j uj. Now we multiply A transpose in front of that. Then A transpose uj. Okay, let's go over there. A transpose uj is sigma j vj. So that A transpose uj will be sigma j vj. So we have here sigma j squared vj. This means that Now, sigma j squared and Vj are a pair of eigenvalue and eigenvector of A transpose A. So that's the claim. Vj, sigma j squared are eigenvector, eigenvalue pairs of A transpose A for j's from 1 to R. Okay. So that's the reason singular values play the role of eigenvalues. Now similarly, now by using the other way, A transpose Uj, okay, A transpose Uj is sigma j Vj, and A is multiplied, then A Vj is now sigma j Uj, so we recheck that. That means here in Uj sigma j squared are eigenvector eigenvalue pair for A transpose. This equation gives us how to find singular values. Of course, after organizing A transpose A, and we try to find eigenvalues and eigenvectors. And after finding eigenvalues, just take a square root, then that will be singular value. And so that by using this equation, we can find singular values and write singular vectors V. Now, if you try to get left singular vectors by using this one, then it's expensive. Once we can get right singular vectors, the Vj, then now here, okay, Vj, then here Avj must be sigma j Uj, so that after multiplication of A divided by sigma j, then we'll get Uj. Right? By using this equation, again, we can find left singular vectors. So therefore, right singular vectors, we have to find eigenvalues and eigenvectors of A transpose A and take a square root for singular values from the eigenvalues, and then use that equation to get left singular values, singular vectors. Okay. Now we have here dyadic decomposition. A is on m by m metric. Then now we have a singular value decomposition. This is another way of writing the singular value decomposition, and this is called dyadic decomposition. And each one from J is 1 to n, each one is rank 1 metric. And this whole thing is addition of sum of rank 1 matrices. Once rank is R, then rather than n, you can write here R. So ignore the portion where the singular value is 0. This property has been utilized for various approximations and applications by dropping singular vectors corresponding to small singular values. Not only 0 singular values, sometimes small portion. If a singular value is very small, then you may ignore, and then by using only first few singular vectors, you can approximate the given information. In fact, A is in application, it may have information. So sometimes it's called information metric or data metric, and so that you can approximate the given information or data by selecting first a few very important the components. Okay. There are many applications using this dyadic decomposition. Now we'll go to geometric interpretation. Here, A, the metric A, maps on orthonormal bases to orthogonal bases. Once you multiply for these bases and A, then we already know that a V1 is a sigma 1 U1, a V2 is a sigma 2 U2, and so on. And if it is rank R, then here the remaining part is 0, so that if we consider a basis, then we have to write up to R. If the 0 vector is involved, then it cannot be a basis. Okay. So A is a map between two bases. The beginning space has orthonormal bases, and then your target in codomain in range we have now orthogonal bases. It's a scaled one. Let's consider a unit sphere in Rn and Sn minus 1. Okay, once n is 2, then there is plane, and S1 is just unicircle, and n is 3, then the unit sphere is S2, which is real unit sphere in 3D, and so on. So consider unit sphere Sn-1, then that is collection of points such that the square sum is 1. Every point and square sum is 1. And you can easily see, for example, in circle, now that is now x squared plus y squared equal 1. So the square sum of component must be 1. In the sphere also the same, x squared plus y squared plus z squared is 1. That is sphere in 3D space, right? So sphere in n-dimensional domain is defined in this way. Then for every x, every point on the sphere, now x can be written in this way, because v1 to vn is a basis, and along with the basis we can write, along with the coefficients, we can write in this way linear combination of the basis function. Now a is multiplied, then av1 is sigma 1 u1, av2 is sigma 2 u2, and so on. We have that. Now for each one, that one, we try to use y notation. There's y1, there's y2, and so on. Okay. Then now, so that eventually, once we are considering this one orthogonal basis, then for y values, we can get some further mathematical information. Okay, yj is a sigma j xj is, okay, that equation is same as xj is yj over sigma j. xj square sum is 1, so that square sum, once is a full rank, then again must be 1. So yj squared over sigma squared, if sigma j up to n is non-zero, so it's well defined, then from 1 to n, summation must be 1. However, now it is a rank R, and once it is alpha, up to R, summation is alpha, then because we miss some components so that it cannot be larger than 1. It can be smaller than 1, anyway, bounded by 1. And then this one is an ellipsoid in the new space. Okay, okay, let's see this example. Here, now in two-dimensional area, so that it's 2 by 2 metric, and we have a singular value decomposition, and now S1 will be transformed, and that's real U sigma V transpose. Now for every x over on S1, the circle of radius 1, the unit circle, we multiply first V transpose and then sigma and U. This is the circle after multiplying V transpose we have there. That is rotation. In fact, it's flipped. Okay, the red, blue, counterclockwise, but it's a blue, red, so it's flipped, but anyway, it is rotated. Now, we apply sigma, then sigma, and in the first coordinate direction is 4 times enlarged. And then in second direction, is almost the same. So you can see here from this one, now in horizontal direction is enlarged. It's 4 times 1306 times enlarged. Okay. Now for that metric U, once U is multiplied, again a sort of a rotation, but then from here to there, again flipped. Okay. So in general, V transpose is a rotation, and sigma is a scaling, and U is again rotation in general. Okay, this is end of part 1, and we'll continue in the second part. Thank you.